Now, continuing with the operators in quantum mechanics, we start off this video with the functions of operators. Now, if we have learned about the operators operating directly, but we have also have the function of operators. So if we have a function f of the operator a, and if a is a linear operator, we can Taylor expand f of a as follows, that is equal to expansion in terms of the Taylor series extending from n is equal to 0 right up to infinity, an and the operator raised to the power n. Now, an is just the expansion coefficient, and as for the we consider the scalar, a is a scalar, uh, then we can expand this as follows, that is e raised to the power a operator. This is a function of a, of course. So what we do there is simply n going from 0 to infinity. So this is just a case. If e raised to the power a times of a operator, then we expand it in terms of the Taylor series as a raised to the power n over n factorial a operator raised to the power n, and that is going to give us the unity operator plus a times a operator plus a squared over 2 factorial a operator squared, and it continues so on for higher values of n. Now the commutators involving the function operators will have a supposedly commutes with b. This is another case. So if we have a commuting with b, then we also have b to be commuting with the function of a. Now f of a commutes with a, and with any other function, let us say we have g of a, then a times of a commuting with f of a, and that is equal to 0, and a raised to the power n also commutes with a f of a, and also we have any other function g of a which is a function of a. We have f of a g of a to be equal to 0 as well. So these are the cases of function operators, and especially the commutators involving function operators. Now if we are to consider the Hermitian adjoint, what we get for the function operators is that if f of a is the function of the operator a, then we consider the adjoint of it. It is simply going to give us the complex conjugate of the function of the adjoint of a. Now if a is Hermitian, f of a may not necessarily be Hermitian. So that is a point that we must note, that if a is Hermitian, meaning that the adjoint of a is equal to a, then f of a is not necessarily Hermitian. But it can be Hermitian if we have the function is a real one. If f is a real function and a is Hermitian, then f of a will be Hermitian. So For example, we can consider e raised to the power the operator of a, and we take the Hermitian adjoint of it. We have e and raised to the power of adjoint of a, and if a is Hermitian, then this function of the operator is also Hermitian. But if we consider the case where e is raised to the power I times of the operator a, and then we consider the Hermitian adjoint of it, then in that case we'll be having, as we can see over here, the conjugate of it. So e raised to the power minus I, and then we'll have the adjoint of a multiplied to it. Now obviously this is not Hermitian because we have a minus over there. It's not the same as the operator itself after carrying out the adjoint operation. Now we can consider another example over here. So if we have supposedly a value alpha multiplied to supposedly a complex number, if alpha is a complex number multiplied to it, and then we have the operator of a, and we take the Hermitian adjoint, then we have e raised to the power minus I, the conjugate of alpha, and then the adjoint of the operator a. So if a is Hermitian, an operator function which can be expanded as f of a will be Hermitian only if the expansion coefficient an are real numbers. But in general, if a is not Hermitian, even if a is Hermitian, which is what we have mentioned over here. Now we'll have some relations that are involving the function operators, and they can be given as follows. That is, the commutation of a with b if not equal to 0, means if they do not commute, then b does not commute with the function of a as well, which we had provided the other way around if they commute. Now if we have the exponential of e multiplied to the exponential of a multiplied to the exponential of b operator, let me just erase that and rewrite that properly for you. So if we have the exponential term over there, then e raised to the power a times of e raised to the power b is simply equal to e raised to the power a plus b, and also we have another term multiplied to it, that is e raised to the power the commutator of a b over 2. And then finally, if we multiply three terms, that is e raised to the power a times of b times of e raised to the power minus a, then we have the series as shown below, and it's a continuous one. Now we move over to the discussion about the inverse and the unitary operators. Now as for the inverse of an operator, now if the inverse of an operator exists, it may not exist, because just like in the case of matrices, we know that operators are matrices. In case of matrices, the inverse of the matrix will exist only when the determinant is non-zero. So likewise, the inverse of the operator must also exist. So if we have the inverse of an operator, then it can be provided as supposedly a inverse multiplied to a will give us a unity operator. Same goes with a multiplied to the inverse of a. And this operator, when operated on the, that is the unit operator, obviously when it is operated on any given state, then it leaves the state unchanged. And if we are looking at the quotient of two operators, then supposedly we consider the quotient of we divide one operator over another operator, let us say a over b, then we have simply that leads to a multiplied to the inverse of b. The side on which the quotient is taken, that matters, because if we must note these things, that if a over B is what we have, then it is simply A over the unit operator over B operator, and that will give us A and B inverse. And supposedly we have the unit operator over B, and then that multiplied to the A operator, then that will give us B inverse times of A. And these are pretty uh, much to be taken care of, because both of these are not the same. A times of B inverse and B inverse times of A is not the same. Always remember the case of matrices. The ordering must be done in the right way. They don't always mean the same in no matter whatever order you put it. So the ordering has to be considered in which order you are putting the operators. Now, considering these ideas, we may mention the following properties of the inverse operator. So if we have supposedly the multiplication of a number of operators, that is A, B, C, and D, and then we take the inverse of the whole of it, then we have simply D inverse times of C inverse times of the inverse of B times of the inverse of A. The ordering is exactly in the opposite sense. And also, if we have A operator raised to the power n and we are taking the inverse of it, then we have simply the inverse of A raised to the power n is also the same thing. Now what about the case of unitary operator? Now remember, unitary and unit are not the same, of course. A unitary operator is one that it is said to be unitary if its inverse is equal to its adjoint. So if we have the unitary operator, the adjoint of it is equal to its inverse, then this is called as the unitary operator. Or if we are multiplying u on both sides, what do we get? We simply get u with the adjoint of u is equal to u adjoint of u, and that is going to give us the unit operator, because multiplying both sides with u we end up with I on this side, and that is what we just put over here. The product of two unitary operators is also unitary. So if we have, that is, the product of two unitary operators is also unitary. That means if we have u and v as the operators, then uv adjoint multiplied to it, then we get this to be as uv, and the adjoint, as you know, when operator goes on the other way around, so vu, and that gives us u v and the adjoint of v, and then u with the adjoint of u, and v adjoint of v is going to be unit operator because that's a unitary operator, and u with u adjoint is also going to give us a unit operator because that's also a unitary operator, which is u. And u this one also, as you can see, is simply u v inverse because they are unitary operators. This can be generalized in a number of ways. If we have number of unitary operators multiplied together, then we can do that with this case. Now we can discuss about a property of the unitary operator by means of this question that we have right in front of us. That is, under what condition, supposedly we have a parameter epsilon and an operator g, and they are put together in the form of an operator u, which is equal to the exponential of I times of the epsilon times of g, and that operator will be unitary under what condition? So if we are to take the case of a unitary operator, then well, that has the property that you will take the Hermitian adjoint of it, and then you will be getting an inverse. If that is if we take the adjoint of it and we get an inverse of it, then that's what we call as a unitary operator. Now we have just studied about the case of function of an operator. So we have the condition that f of a, and when we take the adjoint of it, that is equal to the conjugate of f of the adjoint of a. So from that property, what we get is, if we apply that over here, we get the e, that is the epsilon, not the epsilon, we have e raised to the power I e g, and we take the adjoint of it, then that will give us e raised to the power minus of I, that is the conjugate, and then we have the epsilon and g operator. So this is nothing but equal to e raised to the power I e g, all raised to the power minus 1, which means if we have u, then the adjoint of u is giving, this is u of course, the adjoint of u is giving us u inverse, but that will be only possible when we have this term epsilon to be a real one. If that is imaginary, then this won't be possible. So the important condition is that the epsilon factor that is multiplied to it, that must be real. And also we have the case where g remains as g if it is Hermitian. If it is not, then it's not going to be just g, because g adjoint is equal to g only if g is Hermitian, the condition of Hermitian operator. So first thing is that this has to be real, that is the epsilon factor multiplied to it, and the operator that is in the exponential term, that has to be Hermitian. So these are the two conditions that must be satisfied in order that the operator u is a unitary operator. Now next we discuss about the eigenvalues and eigenvectors of an operator. Now a state vector psi is called an eigenvector of an operator A if it is giving a result as a times of psi, small a times of psi, where small a is a complex number and is known as the eigenvalue of the operator A. Now this equation is known as the eigenvalue equation. Eigenvalue equation or even eigenvalue problem. Of the operator A. Its solution, they yield the eigenvalues and the eigenvectors of A. A simple way to put it, if we have the unit operator to be operating on the state vector psi, then we have the result as 1 times of psi, which is equal to psi, of course. So this means that all vectors are eigenvectors of the unit operator with one eigenvalue, that is 1. Now we have to note a few things, that is, if we have A operating on psi, that is giving us the small a eigenvalue times of psi, then also we'll have the nth power of A operating on psi to give us the n powered eigenvalue, that is A raised to the power n times of psi. And also if we have the function of the operator A to be operating on psi, and that will give us the eigenvalue as the function of the small a times of psi, and this can be obtained. Now all of that is possible only if we have this case. So if we have this case, suppose this is valid and we have as the function we take the exponential case, that is e raised to the power I a operator acting on psi, that is going to give us uh, e raised to the power I times of a, that is the eigenvalue that we consider, times of psi. Now for the eigenvalues of the inverse of an operator, now if the inverse of an operator exists, then the eigenvalues of the inverse are going to be the inverse of the eigenvalues of A. Now let's check that out. So if we have the inverse of A and that operator operates on A of psi, then A inverse of A is going to be a unit operator, and unit operator operating on psi is going to be psi itself. On the other hand, if we are considering the inverse of A and we take it like this, where we first operate A on psi, so that is going to give us A times of, because A has operated on psi, so that is going to give us A times of the inverse operating on psi once again. And as you know, we have both the cases on the left hand side to be the same, so the right hand side terms have to be the same. So what that means is A acting A multiplied to the inverse of the A operator acting on psi is going to give us psi. And what that also means is that A inverse operating on psi is going to be equal to 1 over A times of psi, which means the reciprocal means the inverse of the eigenvalue times of psi. So if the inverse of an operator is existing and the operator has an eigenvalue A, then the inverse of the operator acting on the state vectors will give us the inverse of the eigenvalue as its eigenvalue. Now we put down some theorems pertaining to the eigenvalue problems, which will be helpful. So the first being that for a Hermitian operator, let me write that down first. So for a Hermitian operator, all of its eigenvalues are real, and the eigenvectors, so first things first, this is real, and the eigenvectors corresponding to different eigenvalues are orthogonal. So let's try and prove what we have just said. So what we have is that if we have A as the Hermitian operator and it operates on a state phi n to give us the eigenvalue an times of phi n. An is the eigenvalue, or are the eigenvalues for those n terms. Now we have to prove that all the an, they are real, and as for the orthogonality, we have this to be equal to the Kronecker delta mn. Now first things first, what we do is we operate this on the ket vector and we obtain those eigenvalues. Now if we put the bra vector on the other side, then what we end up with is this. And as for the other way around, we take the adjoint on the bra vector, and then because the eigenvalues are obviously, as you know, complex numbers, so we'll have the conjugate of them, and then we have the bra vector itself. And then we put the ket on the other side over here, then what we get is this. Now if we, what we do is we subtract the second equation, that is this one, from the first equation. So what do we get? Well, what we get is on the left hand side of the equation, because A is Hermitian, so the adjoint of A is going to be equal to A, so the left hand side is going to be 0. As for the right hand side, what we have is we have an minus the complex conjugate of am, and then we have the inner product of the state vectors, that is phi m and phi n. Now that is equal to 0. Now there are two cases which we can consider. Now if m is equal to n, then since phi n inner product is obviously positive term, we have an to be equal to an star, that is the conjugate of it. That means an must be real. Now the second case, if suppose we have m to be not equal to n, then we have an to be not equal to the conjugate of am. Then we must have this, that means that this factor is not going to go to 0. So what we must have is that phi m, the inner product of phi m and phi n, that will have to will give 0. That is a must, which means that phi m and phi n eigenstates, they are orthogonal. So that's the part with that's the proof of the first theorem that we discussed. As for the second theorem, we have the eigenstates of a Hermitian operator. They define a complete set of mutually orthogonal basis states. The operator is diagonal in this eigenbasis with its diagonal elements equal to the eigenvalues. That is when we will be dealing with the matrix part of it, then we can discuss this in detail. But as of now, you must know that the diagonal of the eigenbasis, that will be the elements that will be equal to the eigenvalues. This basis set will be unique if the operator has no degenerate eigenvalues, and not unique if there is any degeneracy. And as for the third and the fourth one, we have that if two Hermitian operators A and B commute, then the operator A having no degenerate eigenvalue, each eigenvector of A is also an eigenvector of B, and therefore we can construct a common orthonormal basis that is made of joint eigenvectors of A and B. Finally, the eigenvalues of the anti-Hermitian operators are purely imaginary or equal to 0. We'll keep these things in mind, these theorems, and we'll be using them in our analysis later on related to the operators in quantum mechanics. That's it from this video. We'll be continuing with one more video at least on the operators, and then we'll move over to the next important stuff on the introductory mathematical tools of quantum mechanics. Till then, thank you for watching.